How did you get on with assignment 8? Though the focus of this course is a particular kind of thinking, rather than any specific mathematics, the integers and the real numbers provide convenient mathematical domains to illustrate mathematical proofs. Those domains are number theory and elementary real analysis. The principal advantage as example domains is that everyone has some familiarity with both systems, yet very likely you won't have been exposed to their mathematical theories. I'll take the integers first. Most people's experience with the whole numbers is by way of elementary arithmetic. Yet the mathematical study of the integers, looking beyond mere calculation to the abstract properties those numbers exhibit, goes back to the very beginnings of recognizable modern mathematics around 700 BCE. That study has grown into one of the most important branches of pure mathematics, number theory. Most college mathematics majors find that number theory is one of the most fascinating courses they take. Not only is the subject full of tantalizing problems that are easy to state but require great ingenuity to solve, if indeed they have been solved, and many haven't, but some of the results turn out to have applications crucial to modern life, internet security being arguably one of the most important. Unfortunately, we'll barely scratch the surface of number theory in this course, but if anything you see in this lecture arouses your curiosity, I would recommend that you look further. You're unlikely to be disappointed. The mathematical interest in the integers lies not in their use in counting, but in their arithmetical system. Given any two integers, you can add them, subtract one from the other, or multiply them together, and the result will always be another integer. Division is not so straightforward, and that's where things get particularly interesting. For some pairs of integers, say 5 and 15, division is possible. 15 divides by 5 to give the integer result 3. For other pairs, say 7 and 15, division is not possible unless you're prepared to allow fractional results, which takes you outside the integers. If you restrict arithmetic to the integers, division actually leads to two numbers, a quotient and a remainder. For example, if you divide 9 by 4, you get a quotient of 2 and a remainder of 1. 9 equals 4 times 2 plus 1. This is a special case of our first formal theorem concerning integers, the division theorem. The division theorem says the following. Let a, b be integers with b greater than 0. Then there are unique integers q and r such that a equals qb plus r and 0 less than or equal to r less than b. Well, there are two parts to this theorem. There's an existence part, there are integers with this property, and there's a uniqueness part. Those integers are unique with this property. In proving the theorem, we're going to take those one at a time. I'll first prove existence, and then I'll prove uniqueness. So, proof. As always, it's a good idea to begin a proof by stating the method you're going to adopt. In this case, what I'll say is I'm going to prove existence first, then uniqueness. I'm not using any standard method, so I'm not able to state that I'm using something like induction or whatever. But it will orientate the reader to say that the first part of the proof will deal with existence and the second part will deal with uniqueness. Okay, so we're going to handle existence. Well, look at all non-negative integers of the form a minus kb, where k is an integer, and show that one of them is less than b. What the theorem says is that among the integers a minus qb, namely the integers r, there is one with r between 0 and b. So I'm going to look at all possible candidates for a minus kb, or a minus qb if you like, and I'm going to show that among those candidates, one of them satisfies that condition. And the k for which it satisfies that condition will be the q that I'll take for the theorem. Well, first of all, I need to show that there are such integers. For example, take k equals negative absolute value of a. Then, since b is greater than or equal to 1, a minus kb equals a plus absolute value of a times b, which is greater than or equal to a plus absolute value of a, which in turn is greater than or equal to 0. Well, having shown that there are such integers by producing a k that gives me such an integer, I can choose the smallest one. Let r be the smallest such integer, and let q be the value of k for which it occurs, i.e. we'll have r equals a minus qb. So with r and q defined in this way, I will indeed have a equals qb plus r. If I can show that r lies between 0 and b in this fashion, then I'll have proved the existence. So, to complete the proof, we show that r is less than b. Well, suppose, on the contrary, that r is greater than or equal to b. In other words, I'm now going to use proof by contradiction to show that r is less than b. Well, if r is greater than or equal to b, then a minus q plus 1b equals a minus qb minus b, which equals r minus b, which is greater than or equal to 0 by virtue of this assumption. Thus, a minus q plus 1b is a non-negative integer of the form a minus kb. But r is the smallest such. And yet a minus q plus 1b is less than a minus qb, which is r. And that's a contradiction. If r is the smallest such, we can't find a smaller one. There's a contradiction. Hence r is less than b, because we obtain that contradiction on the assumption that r is greater than or equal to b. And that proves existence. If you haven't seen a proof like this before, it almost certainly looks very complicated. It's actually not complicated or deep, it's just intricate in its structure. The idea is to look at all of the possible candidates to make this true. Well, first of all, we have to show there is a possible candidate, and we actually do that by exhibiting one. And then, to get a candidate which satisfies this additional requirement, we pick the one where the r is the smallest, it's the minimal value of r that gives us one of these things. And then we use the fact that it's minimal in order to show that it has to satisfy this requirement. Each individual step is just elementary algebra. It's just somewhat intricate to push the argument through. There's a lot of arguments in mathematics like this. There was no deep mathematics involved. There's nothing more than elementary arithmetic and a little bit of algebra. But there's a bit of intricate structure to make the proof work. So if you haven't seen this kind of argument before, it'll probably take you several reads through. You need to look at it several times before it begins to make sense. Okay, well, that proves existence. Then we need to turn to uniqueness. To prove uniqueness, we show that if there are two representations of A equals QB plus R and A equals Q prime B plus R prime, with 0 less than or equal to R and R prime less than B, then R equals R prime and Q equals Q prime. So the first part of the division theorem, the existence part that we've already proved, shows that there are representations of this form. What we're now doing is showing that if there are two such representations, then in fact they're identical. The R is the same and the Q is the same. Incidentally, you probably realise by now that the letter Q is going to denote quotient and the letter R is going to denote remainder. We haven't officially defined quotient and remainder yet, so I haven't written anything like that down, but I'm using the familiar notation. Because what we're doing is we're giving the mathematical underpinnings of the familiar knowledge that you probably have about arithmetic, dividing one integer by another. Okay, so we have an equation here. QB plus R equals Q prime B plus R prime. Let's rearrange it. Rearranging, I get R prime minus R equals B into Q minus Q prime. And I've labelled that equation 1 for later reference. Now I'm going to take absolute values in this equation. And when I do that, I get absolute value R prime minus R equals B times absolute value of Q minus Q prime, which I've labelled equation 2. B is positive, remember. So when you take absolute values, B remains the same. But negative B is less than negative R, which is less than or equal to 0, and 0 is less than or equal to R prime, which is less than B. So negative B is less than R prime minus R is less than B. Well, if R prime minus R is between negative B and plus B, that means that the absolute value of R prime minus R is less than B. So by 2, B times absolute value of Q minus Q prime is less than B. Well, I can divide by B now to give me absolute value of Q minus Q prime is less than 1. But everything here is an integer, and the only way you can have a pair of integers, the absolute value of the difference between them being less than 1, is if that absolute value is 0, which means Q has to equal Q prime. And then by equation 1, R has to equal R prime, and that proves uniqueness. And with it, we've proved the division theorem. Well, again, if you haven't seen arguments like this before, it's going to seem pretty daunting, but when you go through it step by step, this is really just very basic arithmetic arguments with inequalities. Take it step by step, and you should be able to follow the arguments through right to the end. Okay, good luck with that. If this is the first full-blown, rigorous proof of a theorem like this that you've encountered, you'll probably need to spend some time going over it. The result itself isn't deep. It's something we're all familiar with. Our focus here is on the method we use to prove conclusively that the division property is true for all pairs of integers. Time spent now making sure you understand how this proof works, why every step was critical, will pay dividends later on when you encounter more difficult proofs. By gaining experience with mathematical proofs of simple results like this one, which is obvious, mathematicians become confident in the method of proof and can accept results that are not at all obvious. For an example of a result that's not obvious, in the late 19th century, the famous German mathematician David Hilbert described a hypothetical hotel that has a strange property. Hilberts Hotel, as it's become known, is the ultimate hotel in that it has infinitely many rooms. As in most hotels, the rooms are numbered using the natural numbers, 1, 2, 3, etc. One night, all rooms are occupied when an additional guest turns up. "I'm sorry," says the desk clerk, "all our rooms are occupied. You'll have to go somewhere else." The guest, a mathematician, thinks for a while before saying, "There is a way you can give me a room without having to eject any of your existing guests." Before I proceed with this story, you might like to stop the video for a moment and see if you can see the solution the mathematician guest has seen. The clerk is sceptical, but he asks the mathematician to explain how he can free up a room without ejecting anybody already in the hotel. "Well, it's simple," the mathematician begins. "You move everybody into the next room. So the occupant of room 1 moves into room 2, the occupant of room 2 moves into room 3, and so on throughout the hotel. In general, the occupant of room n moves into room n plus 1. When you have done that, room 1 is empty. You put me in that room." The clerk thinks about it for a moment and then has to agree that the method will work. It is indeed possible to accommodate an additional guest in a completely full hotel without having to eject anyone. The mathematician's reasoning is totally sound, and so the mathematician gets a room for the night. The key to the Hilbert Hotel argument is that the hotel has infinitely many rooms. Indeed, Hilbert formulated the story to illustrate one of the several surprising properties of infinity. You should think about the above argument for a while. You won't learn anything new about real-world hotels, but you will come to understand infinity a bit better. And the significance of understanding infinity is that it's the key to calculus, the bedrock of modern science and engineering. And when you're satisfied you understand Hilbert's solution, try the following variants. First variant. The Hilbert Hotel scenario is as before, but this time 2 guests arrive at the already full hotel. How can they be accommodated? In separate rooms, I should add, without anyone having to be ejected. Second variant. This time, the desk clerk faces an even worse headache. The hotel is full, but an infinite tour group arrives. Each group member wearing a badge that says, "Hello, I'm N," for each of the natural numbers n equals 1, 2, 3, etc. Can the clerk find a way to give all the new guests a room to themselves without having to eject any of the existing guests? And if so, how? Examples like the Hilbert Hotel demonstrate the importance of rigorous proofs in mathematics. When used to verify obvious results like the division theorem, they may seem frivolous. But when the same method is applied to issues we are not familiar with, such as questions that involve infinity, rigorous proofs are the only thing we can rely on. Now back to the division theorem. Well, the way I've stated the division theorem, it only applies to division by a positive integer b. There's a more general version that I'll give you now. So, theorem, general division theorem, let a, b be integers with b non-zero. Then there are unique integers q and r such that a equals q times b plus r and 0 less than or equal to r less than absolute value of b. So the general division theorem is almost exactly the same as the previous division theorem we proved, except that instead of demanding that b is strictly positive, we're saying that b is non-zero. And then here we have the absolute value of b. And the proof follows fairly straightforwardly from the previous result. Then
since the absolute value of b is greater than 0, the previous theorem tells us there are unique integers q prime and r prime such that a equals q prime times the absolute value of b plus r prime, and 0 less than or equal to r prime less than absolute value of b. Well, now we simply let q equal negative q prime and r equal r prime. Then, since absolute value of b in this case, with b negative, is negative b, we get a is qb plus r, 0 less than or equal to r less than absolute value of b, and that's this theorem. So we simply threw it back to the previous result. And with the general division theorem now established, we can formally give names to the two numbers q and r. Okay, and officially we say the number q is called the quotient of a by b, and r is called the remainder. And so we've now cycled right back to something that you learned in elementary school about dividing numbers, and that there were sometimes remainders, there were quotients and remainders. Okay, only now we've done it with some sophistication, and we've shown that everything is well defined. Now, how about that? Well, now that we have the division theorem available, we can look at the important mathematical property of divisibility. If division of a by b produces a remainder r equal to 0, we say a is divisible by b. Hence, a is divisible by b if and only if there's an integer q such that a equals bq. For example, 45 is divisible by 9, but 44 is not divisible by 9. The notation that we use for divisibility is this: b vertical line a denotes a is divisible by b. And let me give you a warning at this point. B divides into a, or a is divisible by b, is not the same as b divided by a, with a slanted line. This guy is a relationship between a and b. It's true or false. This guy denotes a rational number. The result of dividing b by a in the rational numbers. So we have a property, a relationship, which is either true or false, and we have a notation for a rational number. Now, these are quite distinct concepts. This is something to do with two integers, tells you whether two integers are in a certain relationship. This is a notation for a specific number. The reason I'm issuing this as a warning is that beginners in particular often confuse these two things. They both, after all, do have to do with division. But in this case, it's a property, has nothing to do with fractions, with rational numbers. This, it's a specific number. It's a specific rational number that we're referring to. Now, there wouldn't be as much of a problem if the notation wasn't very similar. And it gets worse when people with sloppy handwriting, and you've probably noticed that I'm one of them, often don't distinguish clearly between a vertical line and a slanted line. In fact, this one is already almost vertical. Maybe it would have been better if I'd written it like that. Okay, that's better. But because the notation is similar, it's often very easy to get confused between these two things. The context does disambiguate. If you understand what's been discussed, you shouldn't have any problems. But bear in mind, especially when you're meeting this material for the first time, that there is an important distinction here. And in fact, I've got a quiz coming up in a moment, which I hope is going to help cement your understanding of this notion so that you'll be able to distinguish it from this one. Okay, and once we've got divisibility lined up, we can define the all-important notion of a prime number. A prime number is an integer p greater than 1 that is divisible only by 1 and p. Notice that we explicitly exclude 1 from the prime numbers. So the first prime is 2, the next one is 3, then 5, then 7, then 11, and so forth.
Now for that quiz about divisibility.
Okay, how did you do? Well, remember the condition we have to check is this one. B divides A if and only if there is a Q such that A equals BQ. Well, let's see what we have. The correct ones are B, D, F, G, and H. Why don't I have A? Well, remember, the whole definition of divisibility was under the assumption that B is non-zero. We can't consider divisibility by a zero number. So that one doesn't work. And likewise, that one doesn't work. And of course, the reason this one doesn't work is because 7 simply doesn't divide into 44. Okay? Do be careful about this though. Division by 0 is problematic under any circumstances, and so we rule it out. And in this case, it was ruled out in the very statement of the divisibility theorem. Okay? How about this one? Well, again, the condition we have to check is that B divides A if and only if there is a Q such that A equals BQ. And again, this is under the assumption B non-zero. Everything is an integer here. But the correct ones are that, and that. So why are the others false? Well, this one is false because that simply doesn't divide that. However, if you sort of got out a calculator and actually tried to divide it, then you were missing the obvious point. This is an even number, and that's an odd number. And we cannot have an even number dividing an odd number. So if you had to do any arithmetic for this, then you were making the mistake that I've been warning you against of acting as if you were in high school. This is a course about mathematical thinking, and what I hoped you would have done is to think about this mathematically and realize that you can't have an even number divided into an odd number. So this is a cautionary reminder that this is not about jumping into calculations and applying procedures. This is all about thinking about a problem. Okay, so that's false. But I would hope that you would recognize it's false without doing any work whatsoever other than a little bit of thinking. Okay? I occasionally like to slick things like that into quizzes just to keep people on their toes. Well, this one is false, of course, because that's simply not the case that 2n divides n squared. The reason the others are false, well, this is false for various reasons. I mean, it's the same. I mean, 2n simply doesn't divide n squared for various reasons. The reason this is false is because if n can vary over z, then that will include n equals 0. And so we can't have this because we can get a 0 coming in. That includes n equals 0. Likewise for this one. Okay, same thing. So this one fails because 0 is included. If I excluded 0, it would be fine. I mean, the only difference between these two is that this is the positive integers, 1, 2, and 3, and so on and so forth. This one, because it's all of the integers, includes 0. Okay, well, let's move on now. I want to prove a theorem now that gives the basic properties of divisibility. So, theorem, let a, b, c, and d be integers with a non-zero. Then the following all hold. 1, a divides 0, and a divides a. 2, a divides 1, if and only if a equals plus or minus 1. 3, if a divides b and c divides d, then AC divides BD. This is under the assumption C is non-zero, because we can't have divisibility by 0. The division theorem itself excludes the case of division by 0. 4, if A divides B and B divides C, then A divides C, and this is under the assumption B non-zero. Again, we have to exclude the possibility of division by 0. 5, A divides B and B divides A, those two hold if and only if A equals plus and minus B. 6, if A divides B and if B is non-zero, then absolute value of A less than or equal to absolute value of B. You can only divide smaller numbers into bigger numbers, or at least numbers that are no bigger than. You can't divide a number B by something that's bigger than it in absolute value. One more. 7. If A divides B and A divides C, then A divides bx plus cy for any integers xy. Okay, you prove all of these by going back to the definition of divisibility. Now, what I'm going to do is just I'll prove 2 of them as examples. Let me just pick number 4. Let's prove 4, that's this one here. All the proofs are essentially the same idea. If A divides B and B divides C, then that means there are integers D and E such that B equals DA and C equals EB. That's the definition of divisibility, in which case C equals D times E times A, which again by the definition of divisibility means A divides C. Let me do one more. Let me do 6. Okay. So A divides B, so that means, since A divides B, it means there is a D such that B equals dA, in which case, taking absolute values, absolute value B equals absolute value D times absolute value A. And since B is non-zero, we know that the absolute value of D will have to be greater than or equal to 1. So the absolute value of A is less than or equal to the absolute value of B. Okay. See, B is non-zero, so D can't be 0, so its absolute value is greater than or equal to 1, and if the absolute value of D is greater than or equal to 1, then A has to be less than or equal to B. The other statements in the theorem are proved similarly. You just take it back to the definition of divisibility, and when you know that, remember the definition is B divides A if and only if there is a Q such that A equals BQ. And in all cases you go back to the definition and then the thing drops out in a couple of lines. Okay, well that's the that lists all of the basic properties of divisibility. Okay, it's time to prove the fundamental theorem of arithmetic. Theorem: every natural number greater than 1 is either prime or can be expressed as a product of primes in a way that's unique except for the order in which they are written. For example, 4 is 2 times 2 or 2 squared, 6 is 2 times 3, 8 is 2 cubed, 9 is 3 squared, 10 is 2 times 5, 12 is 2 squared times 3, and so on and so on. 3,366 equals 2 times 3 squared times 11 times 17, and so forth. I worked that one out in advance, by the way. Okay, so 2 itself is prime, 3 is prime, 4 is a product of primes, 5 is prime, 6 is a product of primes, 7 is prime, 8 is a product of primes, 9 is a product of primes, 10 is a product of primes, 11 is a prime, 12 is a product of primes, and so on and so on and so forth. The expression of a number as a product of primes is called its prime decomposition. And when you know the prime decomposition of a number, you know an awful lot of information about that number and how it behaves with relation to other numbers. Well, we proved part of this a little while ago, proved the existence part. Though I'm going to give you another proof of existence in a moment, but the new part is to prove uniqueness. The uniqueness proof will require Euclid's lemma. That says, if a prime P divides a product AB, then P divides at least one of AB. The proof of Euclid's lemma is not particularly difficult, but it would take me outside the scope of this course. Remember, the focus of this course isn't to teach you number theory and number theoretic techniques, it's to develop mathematical thinking. And it would be too much of a detour from that goal in order to prove Euclid's lemma. But if you just Google Euclid's lemma, you should be able to find some references that would lead you to a proof. Let me give you the existence proof. More precisely, let me give you a new proof of existence. Remember, this is the statement of the theorem. Any natural number greater than 1 is either prime or can be expressed as a product of primes in a way that's unique except for their order. and we're going to prove existence. The previous proof of existence that I gave you used the method of mathematical induction, and I gave it as an illustration of the method of induction. But I'll give you a different proof now. I'll prove it by contradiction. Suppose there were a composite number, that's a non-prime, that could not be written as a product of primes. Then there must be a smallest such number. Call it n. Since n is not prime, there are numbers a, b, strictly between 1 and n, such that n equals ab. If a and b are primes, then n equals ab is a prime decomposition of n, and we have a contradiction. Because n was chosen so as not to have a prime decomposition. It was actually the smallest number that didn't have a prime decomposition. Well, if it's not the case that a and b are primes, then at least one of them must be composite. But if either of a, b is composite, then because it's less than n, it must be a product of primes. So by replacing one or both of a, b by its prime decomposition in n equals ab, we get a prime decomposition of n, and again we have a contradiction. That proves existence. That's the first part of the proof of the fundamental theorem of arithmetic. Now let me prove uniqueness. So what I have to prove is that the prime decomposition of any natural number n greater than 1 is unique up to the ordering of the primes. And I'll prove it by contradiction. So assume there is a number n greater than 1 that has two, or more in fact, different prime decompositions. Let n be the smallest such number. Let n equal p1 times p2 times times pr equals q1 times q2 times qs be two different prime decompositions of n. So we have n as a product of r primes, and we also have n as a product of s primes, some of the primes being different. Well, p1 is a prime factor of n, so p1 divides n, so p1 divides this product. Since p1 divides q1 times q2 through qs, and let me stop at this moment and see what I've done. I've said p1 divides n, so p1 divides this, and I'll split that into two that way, and notice that p1 divides q1 times that, and I've done that in order to apply Euclid's lemma. So now let me continue that sentence. By Euclid's lemma, either p1 divides q1 or p1 divides the product q2 through qs. Remember, Euclid's lemma says that if I have a prime number p, and if p divides a product a times b, then p divides at least one of ab. So Euclid's lemma was that if p divides a product ab, it divides at least one of those two numbers. So from here, p1 divides this product. I've now written that as a product of two numbers, and I can now apply Euclid's lemma and say that if p1 divides that times that number, it must divide at least one of them. Either p1 divides q1, or it divides the other part, or maybe both of them. Okay? Hence, either p1 equals q1, or else p1 equals qi for some I between 2 and s. Okay? If P1 divides Q1, then they're both primes, so the only possibility is that P1 equals Q1. Or else P1 divides this product of primes, which means that P1 actually is one of those primes. So first case, I know that P1 equals Q1. Second case, I know that P1 equals Qi for one of the i's between 2 and s. But then we can delete P1 and Qi from the two decompositions in star, which gives us a number smaller than n that has two different prime decompositions, contrary to the choice of n as the smallest such. Okay, having established that P1 is equal to one of these Q's, we don't know which one, but it's going to be one of them, I can delete the P1 from here, I can delete the appropriate Q from there, and when I delete P1 from there and some Q from there, I still have equality, I still have a prime decomposition of a number, but having deleted that common prime, the number that I get is smaller than n. So I get a number smaller than n that has two different prime decompositions. The number smaller than n will be P2 times times PR, so that will be the number smaller than n. And I've deleted a number from here, and what's left is the prime decomposition here. So the proof involves simply identifying the fact that, or recognizing the fact, and this uses Euclid's lemma, that you're going to have the same prime on both sides. You can delete it and get two different decompositions of a smaller number. And that proves uniqueness. Okay, well, now we've proved the fundamental theorem of arithmetic. Cool, huh?
So, did that make sense? Chances are you're going to have to spend some time trying to come to grips with this. Though I know you're familiar with arithmetic, especially whole number arithmetic, this is probably the first time you've tried to really analyse numbers. See how you get on with assignment 9.